what is control volume, what is system. We have seen what is Reynolds transport theorem. We have applied this Reynolds transport theorem. Normally the main reason for the pressure drop in the pipe is actually because of the friction between the pipe material and the fluid. Okay, suddenly let us suppose if fluid starts entering the small pipe actually for some exit to the pipe, then the fluid suffers some loss. Total energy of the fluid at this location should be equal to the losses that happened plus the total energy available at this location. This is the fourth lecture of this module, control volume analysis. Okay, so we have finished 3 lectures in this case. Yeah, audible, right? Fine then. So we have done with 3 lectures. We have seen basically certain things like what is control volume, what is system. We have seen what is Reynolds transport theorem. We have applied this Reynolds transport theorem to mass conservation, momentum, and also the angular momentum conservations we have applied. And also we could see some things like applications of this linear momentum equation and also the angular momentum equation. Okay, so there is 2 other cases also which we shall discuss. So in today's session mainly we will talk about this one or two cases of what we have to discuss in this angular momentum equation, and then we will look at some minor losses in flow in pipes basically. Okay, so normally when there is some fluid flow, normally the main reason for the pressure drop in the pipe is actually because of the friction between the pipe material and the fluid. Okay, so because of this friction there is certain pressure drop from one location to another location in the flow, and normally what happens is to keep this pressure, we whenever you want to transport fluids to large distance, actually normally if you see in case of oil companies, like when I worked with HPCL, we have a pipeline of around some 700 kilometers length. Okay, so in such 700 kilometers long length, what happens, there is certain pressure drop that happens. Okay, so to compensate the pressure drop, because if the fluid has to flow, there should be certain enough amount of pressure. So normally every 50 to 100 kilometers in between there, we will keep one booster pump locations. Okay, so there will be pumps such that the fluid enters the pump and again it actually increases the pressure of the fluid. Okay, so the main reason is basically this pressure loss is due to this friction. Okay, but sometimes there are some other losses as well, like for example when suddenly a fluid is entering a small pipe. Okay, means let us suppose you have a large tank, suddenly let us suppose if fluid starts entering the small pipe actually for some exit to the pipe, then the fluid suffers some loss. We will see why there is certain loss and all these things. So we will discuss those minor losses in this case, and also we see at some flow measurement devices like the Venturi meter. Okay, we will see the oil phase meter. These are the 2 major meters, and we will also look at some flow nozzle meter also. Okay, so let us try to start our analysis. So angular momentum equation, if you continue. Okay, so first of all, if you do the revision, we have done this RTT, basically Reynolds transport theorem, for which the equation is given by something else, dB by dt of the system, means basically the mass what you have taken. So this is equal to dou by dou t of integral over the control volume totally. Actually this is a triple integration. Okay, we are doing along the volume, so triple integral beta times ODV is what you have. So this plus integral over the complete control surface beta times rho V R bar dot n cap dA. This is what we have seen actually. Okay, so this is basically the Reynolds transport equation that we have looked at. Okay, so we applied this equation to mass of conservation basically. So at steady state we have seen at steady state. So basically when you are doing this steady state, then in such case this term is basically 0, correct? So this first term which is here will turn out to be 0 in case of steady state. And then if you see for mass conservation, let us write the case. So for mass conservation we have seen this mass conservation. In case of this mass conservation, okay, you have seen this control surface over the control surface, this beta times of rho V R bar dot n cap dA, this term is equal to 0 is what we have seen, because if you see this mass conservation, there is no change in the system because this B itself is the mass. So when you're talking about a system, there is no change in the mass, so this is 0. In second, we have talked about this linear momentum equation. So if you see, we talked about the linear momentum, that sigma f on fluid, normally if you write the vector on fluid, this is equal to integral over the control surface, means all over the control surface wherever is the mass interaction across the system, across the control volume actually. So integral over the control surface, velocity, of course the relative velocity times this rho V R bar dot n cap dA. Okay, so V R bar dot n cap dA is what we have seen. And also if you see along the angular momentum case, if you see, let us write here. So angular momentum equation. So if you see this angular momentum equation, so if you see this angular momentum equation, then we have net torque acting on any fluid is equal to, on fluid is equal to this integral over the control surface r bar cross v bar multiplied with rho v relative velocity cos n cap dA is what you have. Of course, here also the relative velocity everywhere. Okay, wherever you find velocity, that is relative velocity. So these are the three equations, the fundamental equations that we have seen, and we try to apply these fundamental equations to all the examples that we discussed in the previous case. Okay, there are two more things which are left over, so let us continue them. So if you see, let us suppose you have a sprinkler of this shape. Okay, so let us suppose you have a sprinkler which has a pivot, means basically the point to which there is entrance. So let us suppose there is some small point of entrance, for example. Now from this point you have fluid is actually entering this and leaving this case. Similarly, so if you see carefully here, so let us suppose if the fluid actually touches it. So let us suppose this is how we have the flow basically here. Okay, so let us suppose there is some sprinkler. So let us suppose this length, or basically if you see, all these are connected by some circular path actually. Okay, so these are connected by some circular path. Let us do one thing. Okay, rather than drawing this way, because you see we'll have certain, let us draw some neat diagram, so that let us spend some time on writing this, because it's not looking good. So okay, so see here, okay, so let us keep some small opening at the center for the fluid in and outflow. Okay, so let us keep it for fluid in and outflow. So let us suppose one, so here before going there, so let us see, let us keep some small openings. I just want to show this as some dotted cycle, that's it. Okay, so let us see some dotted cycle here. Okay, so let us suppose you have some dotted cycle here. Okay, so fine. So if this is the case, now let us suppose to this sprinkler we have three arms. One arm of the sprinkler, second arm for example, and let us suppose you have one more arm of the sprinkler. So let us suppose there is some sprinkler like this. Okay, so that this sprinkler is actually rotating. Now let us suppose if this sprinkler is rotating in the clockwise direction, for example, this sprinkler is rotating in the clockwise direction at angular velocity omega. So let us suppose through the center there is some discharge which is coming into the sprinkler, and this discharge is going into three equal parts, q by 3, q by 3, and also you have some q by 3. So these are the discharges into three equal chambers that are available. And let us suppose the mean radius of this is basically, the mean radius is capital R, for example. Okay, so let us suppose the mean radius is actually capital R in this case. Mean radius is capital R, and let us suppose this diameter is basically small d, for example, of each arm basically. So total there are three arms, each arm is of some small diameter d, and of course if you see this from this pivot which is at the center, from this pivot, if you see, this fluid is being sprinkled at a velocity at a distance of capital R. Okay, now if you see, for example, net torque acting on the sprinkler is 0, means basically if I ask you what is the steady state rotation speed, steady state rotation speed, steady state rotation speed. Okay, so let us suppose if I ask you what is the steady state rotation speed actually here. So let us see, net force acting on the fluid, net force or net torque actually acting on fluid is equal to, because if you see, if this has to rotate at steady speed, then there should not be no torque, there should not be any torque on the sprinkler actually, correct? Because what happens if there is some torque on the sprinkler, then it starts gaining some acceleration. Okay, so alpha should not be there, it should rotate at steady state speed. So whenever it is rotating at steady state RPM, let us try to get the value for different things here. Okay, so sigma t on fluid is equal to, now if you see, all these three are identical, correct? Now see carefully here, at this location, for example, at any location, if you see in general, here the velocity of the flow, for example, is in this direction, for example, say in this direction. Okay, so the flow is coming out in this direction. So whenever the flow is coming out in this direction, if you see, this flow can be resolved into this tangential component and also the normal component actually, correct? So let us suppose if this is oriented in such a way that, let us suppose if the fluid is coming in this direction, so let us suppose it has some tangential component. Okay, so it has some tangential component of the velocity of the flow, and also it has some normal component of velocity. So it has some tangential component which comes here and normal component which actually comes here in this case. Okay, so in that case, only this tangential component velocity is responsible for the rotation of the sprinkler, correct? Because only this tangential component basically facilitates some torque on this. Okay, so let us suppose this is VR or V, for example, velocity of the jet that is coming out, or velocity of the fluid, or generally V, let us suppose. Then because of the rotational speed, if this is R, then definitely there is this tangential velocity of the sprinkler which is in this direction, so which is R times of omega actually, correct? So if you see, whenever the fluid is coming, this fluid is having some tangential velocity V at this location, and also it is having some velocity which is R times of omega to this case. Okay, so if this is the case, let us suppose if this angle is theta, for example. Okay, so with horizontal or with this direction, let us suppose if this angle is theta, with vertical, if this small angle which is theta here, then this is V sin theta. Let us suppose with this along the with the center line, let us suppose along the radius, the angle made by the velocity component with radius is theta, then this is V sin theta, if V is the fluid velocity which is coming out. Okay, so V sin theta and R omega are this in opposite directions. Now since this situation is same at any of the arm, now if you write this sigma t on fluid, then this is equal to, first, m dot out V relative velocity into R at the outlet minus m dot in V relative velocity into radius at the inlet. So you know one thing, that this radius at the inlet is basically 0 here, correct? So this radial velocity at inlet is 0 because fluid is actually coming from the pivot which is actually at the center. Okay, so this radial inlet is 0. Now coming to the radial outlet, if you see, coming to this part, for example, so the total discharge is Q by 3. So Q by 3 times of rho into Q by 3 times of, this is the mass flow which is coming out to this section, into relative velocity. So what is the relative velocity? Basically this is the tangential component which is trying to rotate this, and this is the basically velocity of the arm in the opposite direction tangentially. So the net velocity at this point in this directions is V sin theta minus V sin theta minus R times of omega. Okay, let us suppose if I define angle with respect to this, then this becomes V cos theta. Okay, here I have taken this angle theta is between the flow direction and the radius. Okay, for example, if you take the angle between flow direction and tangent as theta, then this will be V cos theta. Okay, simple resolution. So V sin theta minus R omega multiplied with, now what is the radius at which it is coming out? This point is at a distance of capital R, so this is basically capital R is what you have. Okay, so this is the total outlet of this part. If you take any other arm, the situation is similar. So total momentum is basically 3 times of this, correct? So this is 3 times of this. Now if this has to operate at steady speed, so steady rotation speed, so steady state rotation speed, then definitely if this sprinkler has to rotate at some constant RPM, then definitely net torque acting on the sprinkler should be how much? So please tell me, if the sprinkler has to rotate at constant RPM, there should not be any angular acceleration. So you know T is equal to I alpha. So basically, if this alpha has to be 0, means if the sprinkler has to rotate at uniform speed, then what should be the net torque acting on the speed on the sprinkler? So please tell me, what should be the net torque that's acting on the sprinkler? What should be the net torque acting on the sprinkler if alpha has to be 0? If this has to rotate at some constant RPM, then in such case, what could be the case of sigma T? Torque acting on the sprinkler. Yes, it is 0, correct? So basically, if you see, this is 0. T is basically 0. So similarly here, if you see this is, then definitely sigma T on fluid is also 0. So obviously all these terms doesn't show any impact. So this implies V sin theta should be equal to R omega. So what about omega? V sin theta by small r is the case. Okay, but how you identify what is V? This small diameter is given, correct? So discharge Q by 3 is equal to through this small arm of diameter d, the area of the flow is pi by 4 d square into velocity is V. So what is the expression for V? Basically 4q by, so if you see, velocity has this expression 4q by 3 pi d square. So 4q by 3 pi d square into sin theta divided by capital R actually here. Okay, so this is what we have for the constant angular speed omega. But please be careful, here I have taken the angle theta between the flow direction and the tangent. Okay, so sorry, flow direction and the radius. If angle is given between flow direction and tangent, this angle, if this is theta, then this will be V cos theta obviously, because if you resolve, that's the case, then you will get cos theta here. Okay, so this is the steady state angular speed in this case of a sprinkler. Clear? So this implies, you know, omega is equal to 4q sin theta by 3 pi r d square is what you have here. So this is the value in radians per second, of course. So is this clear to all of you? Okay, so this is the case. Okay, provided this is the angle. Okay, if this is the angle, then it is cos theta. Clear to all of you? Did you understand how I have written this? Because the fluid has a tangential velocity of V sin theta, but this R into omega should be in this case. Okay. So is this clear to you? So type in the chat box. So please type in the chat box. Is this clear to you? Okay. Simple analysis that we have, you know, we generally see all the time. Now let us see one more case of these pipes actually, because I thought of giving you this also. So see here. Let us suppose you have a pipe. Okay, so you have some pipe bend. Okay, force acting, you can like put a heading, force acted by the fluid on a pipe bend. So let us suppose this is some normal thing that you find in normal books, and you know, sometimes in exam they can ask you if you want. Force acted by the fluid on a pipe bend actually. Okay, so let us see here how this is a pipe bend. So let us suppose there is some pipe bend. So let us suppose this is the case. Okay, so let us suppose if this is the case, for example, there is some pipe bend that you have. Normally in homes you see pipes will be bent at some locations if there is no straight path available. Then let us suppose in this there is some fluid flow. Okay, now your control volume is to understand what's happening in this volume. Okay, so let us suppose if there is the case. So this is the control volume. Clear? So this is the control volume that you have. Now try to understand this. Because of the flow, there is some pressure P1 which is acting at this section, and also there is some pressure P2 which acts at this section. Okay, and outside atmospheric pressure gets cancelled because atmosphere acts at every point on this surface, so atmosphere pressure gets neglected. Okay, so therefore if you see, this area is A1 for example, and the pressure is P1. Okay, similarly this pressure is P2 and here the area is A2. Now let us suppose if the velocity of the flow at this section is V1 and velocity of the flow at this section is V2 for example. Okay, so this is V2 in this direction for example, if the pressure is if the velocity is V2. Okay, now let us try to understand this, what happens in this case. So if you see, obviously because of the fluid, when it's flowing, it will exert some force in this direction. Okay, so normally you know this force will be in this particular direction, means as per your understanding, just on the basic understanding, nothing fluid mechanics, no no equations. Normally you understand that whenever fluid is going and hitting this, the fluid will come and hit this section, so obviously there will be some downward force in this direction, correct? So if you resolve, obviously you will get the force in this way, Fx, the x component of the force, and obviously Fy here. Okay, so we have Fy, so this is F, so this is Fx and this is Fy. Clear? So Fx and Fy. Now let us calculate the components, Fx and Fy components. So let us see that. So first of all, if you see sigma F acting on the fluid for example, look, try to understand. Let us suppose if force acted on the fluid, if force acted on the fluid in x direction is Fx, let us suppose we are defining xy coordinate system in this direction, xy coordinate system in this direction. Now let us suppose force acting on the fluid, sigma F on fluid is equal to, in the x direction, so sigma Fx acting on the fluid, sigma Fx on fluid is equal to, look, let us suppose if this bend angle is theta for example. Okay, so let us suppose if this inclination of the bend is theta. Okay, so let us suppose this inclination of the bend is theta, Now see carefully here, in this case sigma Fx of fluid, if you take net force acting on the fluid, so first of all one thing is very clear, this P1 into A1, so this P1 into A1 is the force which is trying to push this fluid, correct? Obviously whatever the fluid that is present here, this will try to push this fluid for the flow, so there is this P1 into A1, so P1 into A1. Next, this P2 is in this particular direction, so see the force P2 A2 is in this particular direction. Okay, so P2 A2 is in this direction, this is P2 A2, but if you see the inclination of this force with horizontal is theta, correct? This angle is theta, so in the x direction if you take, we have P2 A2 cos theta is what you have here, correct? Because you see this is P2 A2 and the angle made by this line with horizontal is theta, so this is P2 A2 cos theta in the negative direction, and obviously here also P1 A1 P2 A2 sin theta. Okay, so we have P2 A2 sin theta is what you have. Okay, so P2 A2 sin theta. Now see here, P1 A1 is acting in the positive x direction. Next, P2 A2 cos theta at this point is acting in the negative direction. You see this is towards the negative side, so minus P2 A2 cos theta. These are the forces due to fluids. Now what happens, the fluid also exerts some force on the bend, so as a result the bend will also exert some force back onto the fluid. So let us suppose that's we are taking in the positive direction for example, so this is Fx on fluid by bend, Okay, so let us suppose this is acting in the positive direction, we don't know what is the direction, so let us suppose that's acting in that direction. Okay, so this is the total force which is acting on the fluid in the x direction, correct? So two pressure forces, this pressure force and also this pressure force at the same time, because of the bend there is some force that actually acts. So this is equal to m dot v out in the x direction minus m dot v in in the x direction, correct? This is the momentum equation that you have. So if you simplify, what is this V out in the x direction? Fluid is going out in V2, so definitely this term is V2 cos theta, and this inlet is V1 because you see fluid is straight away moving in this direction. So if you simplify this result, then let us see what happens. So this implies Fx on fluid by bend, Fx on fluid by bend, Fx on fluid by bend is equal to, this value is equal to, look, if you shift these terms to the other side, we have P2 J2 cos theta minus P1 A1 plus m dot times, m dot is common, so V2 cos theta minus V1. So m dot can be written as either rho A1 V1, or it can also be written as rho A2 V2, whatever you like you can write. So therefore if you see these equations, this term plus m dot times of V2 cos theta, so that can be written as m dot can be written rho A V2, so V2 square cos theta minus, at the same time that m1 can be written as rho A1 V1, so this is rho A1 V1 square. So this is the force X acting on fluid by the bend. So if you want to calculate force exerted by the fluid on bend, take a minus sign of this. Therefore you can understand, therefore sigma Fx, or Fx basically, if you see Fx by fluid on bend, pipe bend is equal to, how much is this? Just inverse of this, correct? Because this by fluid is nothing but minus of on fluid. So therefore if you take a minus sign, we get P1 A1 minus P2 A2 cos theta plus A1 V1 square minus rho A2 V2 square cos theta. So this is the expression for the net horizontal force that's acted by the fluid on the bend actually. Okay, so this is how we get the expression for the Fx by fluid on bend actually. Okay, so this term is a bit important for us. Okay, now because sometimes they can ask you, I don't ask you to remember the formula, but if you know how to write this equation, just within 2-3 steps you can get to this particular value. Okay, next if you want to calculate in the y direction, let us see sigma Fy on fluid is equal to, of course if you see sigma F acting on the fluid in the y direction is equal to, now in the y direction if you see at the inlet there is no force, but at the outlet there is a force. You see P2 A2 sin theta, which is in the downward direction. Okay, so here y is in the positive direction, so but this is in the downward direction. So if you see minus P2 A2 sin theta minus P2 A2 sin theta. Okay, so that's the only force, plus let us suppose the force acting on the fluid is in the positive direction. Let us suppose you take that, so plus Fy on fluid by bend. So these are the total forces which are acting in the y direction. Okay, neglecting the weight of the fluid. Okay, weight of the fluid is neglected compared to these pressure forces, because pressure forces and all, they are very in kilopascals, so they are very large actually. Okay, so now if you see plus Fy on fluid by bend, so this is equal to m dot V out in the y direction minus m dot V in the y direction. Now if you see at the inlet there is no velocity in the y direction, because at the inlet of this volume you see fluid is coming in at velocity v1 straight away. Okay, so there is no y component of velocity, but now if you see this v out in the y direction, so this value is nothing but, at this point you see if you resolve this, for example this is v2, so if you resolve v2 cos theta and v2 sin theta is vertical, correct? So v2 sin theta, V2 sin theta. So from this equation you can understand that, force acted on fluid by bend in the y direction, Fy on fluid by bend, Fy on fluid by bend is equal to, so if this term is equal to, if you shift this term to the right hand side, P2 A2 sin theta plus this m dot V2 sin theta. this is what you have basically. So in both the terms you have sin theta term. So P2 A2 sin theta plus m dot V2 sin theta is there. So here this implies, or this is equal to P2, or you can generally see this implies Fy on bend by fluid is equal to minus of this quantity, correct? So minus of P2 A2 plus this m dot can be written as rho A2 V2 square times sin theta. This sin theta is all over, so this can be written as sin theta. So this is Fy on the bend because of the fluid. Okay, so this is the equation for the force which is acting on the bend in the y direction. Clear? So this is the force acting on the bend in x direction, and this is the force acting on the bend in y direction. Obviously, see, all these terms are positive, so force acting on the bend will be negative, which we know normally from our understanding Fy will be downwards in general. Okay, so once you got Fx and Fy components, if you want the magnitude of the force acting on the bend, then this is equal to root of Fx square plus Fy square, correct? And if you want theta, you know theta is tan inverse of y by x, is also, you can sorry, Fy by Fx, tan inverse of Fy by Fx is what you have actually. Okay, so that's how we have the magnitude of the force and also theta value basically, because normally if you see you want to know the direction of the force. Okay, so how do you know the direction of the force? If force makes an angle theta with horizontal, then tan theta is nothing but Fy divided by Fx. So tan theta is equal to Fy by Fx component, so theta is tan inverse of Fy by Fx. Okay, so that's how you have the theta component and magnitude of F component. Clear? So this is Fy on the bend, and this is the expression for Fx on the bend. Look, just my intention is to tell you that the pressure acting on this particular fluid. Okay, outside everywhere there is atmosphere, so the net effect of the atmosphere gets cancelled all over. Okay, because at every point on the pipe there is some atmospheric pressure, so definitely the atmospheric pressure will cancel out, right? So that's the reason. Okay, so is this clear to you? Force acting by the fluid on the bends. Normally when you have some pipe bends and all, that's how you calculate. Okay, normally not asked in gate examination, but sometimes in descriptive exams like ESC mains or something, they can ask you if they want to. Okay, so that's why I have given you this. Clear? So I hope it's fine to you. If you want to take some note, you can take, or else it's fine. Okay, just even you yourself can also write these equations. Okay, this is, look, don't confuse between this term and this term. This is only due to bend, but this is total force. Okay, this is summation, effect of all the forces. This is just only one of the components of that force. Clear? Now let us see this case of minor losses. Okay, so let us see minor losses in pipes. So let us try to understand what are these minor losses in pipes. So see here, suddenly whenever there is some enlargement in the pipe, so let us straight away start this. First one, sudden enlargement in pipes. Okay, so sudden enlargement in pipes, sudden enlargement in pipes. So see here, let us suppose there is some pipe which is going, now let us suppose suddenly the pipe got enlarged. Okay, means the diameter suddenly increased. Okay, so see here, this is of diameter d1 or a1 area, let us say directly, and let us suppose this is of area a2, for example. This is of area a2. Okay, so we have pipe of area a1 and suddenly it got enlarged to a2, for example. Now let us suppose if you take the flow, so if you see, for example, if there is some flow, the flow happens in this way. So see here, the streamlines will come like this, and they find that there is some space, so they actually go like this. Okay, similarly here also they will find that there is some space and they'll go like this. Okay, similarly at all the points. So like this. Okay, why actually streamlines cannot actually bend sharply? Because the inertia of the flow will try to continue to maintain its flow actually after some time even. Okay, so here if you see, even whenever there is some tight flow, the flow actually gets released here, but it takes some span to get covered this fully. Okay, so that's why. Meanwhile, I want to explain you one very important concept here. At this location, normally what happens when initially when the fluid starts flowing, here if you see, there is some part of the fluid which gets stuck here. Yes or no? That there is some part of the fluid which actually gets stuck here. Similarly here, once the flow got maintained, okay, means in the initial time there will be some fluid which is present here, and then it gets stuck like this. So because of these fluids, there is certain pressure that actually acts on this layer of the fluid here. Okay, so this pressure is given by some P dash actually. It actually acts in this direction, normal to this because of the weight. It's just like a reaction force. Okay, so there is some pressure which is here. So this is called P dash, generally P dash, which is present here. Okay, so this is P dash. Okay, now if you see, if you take a control volume, for example, if you take a control volume, let us suppose if this is the control volume, which is actually here. So if you see, along this flow, if you take, so this is my control volume, for example. Okay, basically along the flow. Okay, now if this is my control volume, now let us see if this section is 1 for example. Okay, so let us suppose if this section is 1 and this section is 2 1 and 2 is the things. Okay, so 1 and 2. Now basically whenever the fluid flows from this point, let us suppose if this is irrotational flow, so let us suppose if you take these 2 points, then, and obviously there are infinite number of streamlines which actually flow, so obviously this is also covered with streamlines, actually very closely spaced. Okay, now if you see, if this point, if I call this 1 and if I call this point 2 for example, then whenever the fluid actually travels from this position to this particular location, then definitely there is some loss. That's what we are calling the sudden loss. Okay, or the minor loss, basically due to sudden enlargement in the pipe. Now what is the loss that actually that is there present here? Okay, so let us see. First of all, from continuity equation, actually if you see this continuity equation, then since the flow is incompressible, because let us suppose if there is some velocity of the flow but not at Mach level. Okay, so let us suppose if there is some flow. Now whenever there is some flow at this point, at this section, let us suppose if the velocity, uniform velocity is v1, and at this section if the uniform velocity is v2, then a1 v1 is equal to a2 v2, correct? So as per continuity equation, if you see, a1 v1 will be equal to a2 into v2, correct? That's what we have. Now if you see, if you want to calculate the loss that happened in this case, so applying Bernoulli's equation at 1 and 2, applying Bernoulli's equation at 1 and 2, points 1 and 2, at points 1 and 2, at points 1 and 2. Okay, now let us suppose we have a pressure which is acting here, obviously because if you cut the pipe, then definitely you have some pressure from this surrounding fluid which is P1, and let us suppose here the area is A1 as we have taken. Similarly at this location the pressure is P2, the pressure at this section is P2, and of course this area is A2. Okay, now if you apply the Bernoulli's equation, we have P1 by rho z plus V1 square by 2z plus Z1 is equal to P2 by rho z plus V2 square by 2z plus Z2 plus there is some loss which is due to this sudden enlargement. Okay, so this is loss. How we have written this? Total energy of the fluid at this location should be equal to the losses that happened plus the total energy available at this location. Correct? So whatever is the energy available here, that is spent in two parts. First part is the loss that happened during this fluid flow. Second part is the storage of energy at this point. Means basically whenever the fluid reaches this point, it still has some energy. So that's basically the energy. So we have taken the total energy at this location 2 and this is at location 1. Now since these 2 points are on the same horizontal level, you know this Z1 and Z2 are actually same. We can cancel them. Clear? So now if you see, this HL is equal to P1 minus P2 by OZ, P1 minus P2 by rho z plus V1 square minus V2 square by 2z. Correct? V1 square minus V2 square by 2z. Now you have to identify, of course V1 and V2s can be identified. So normally velocity in the pipe, if the diameter is known, discharge is known, you can calculate velocities. Okay, from continuity equation you can calculate V2 also. But how to identify this pressure difference, that's we have to focus on. So let us see here. Let us try to find some expression for this P1 minus P2. Okay, now let us apply the linear momentum equation. Okay, so let us apply linear momentum equation for this control volume. So then you will try to understand this. See here, applying linear momentum equation for the control volume. Applying linear momentum equation for the control volume. For the control volume. For the control volume. So let us apply that. Okay, so applying linear momentum equation for the control volume. Now see, sigma fx on fluid. Sigma fx on fluid is equal to, so what is sigma fx? You see, for example, if you take this as positive x direction and you take this as positive y direction, for example, and then let us see what happens. At this point you have this P1 into A1 in the positive direction of x and P2 into A2 in the negative direction of x. Okay, so P1 A1 minus P2 A2, and also if you see, there is some pressure which is actually acting on this fluid. Correct? So this pressure is acting on this fluid along this part, actually till this particular point. If you see, till this particular point, if you see along this length, this pressure is acting. Okay, so what is the area? If you see this P dash, if you resolve, normally if you see, P dash on the top part is in this way and P dash on the bottom part is in this way. So if you resolve, both these components will be in the horizontal direction and both these components will be in the vertical direction. So these two will cancel each other because they are just in opposite direction to each other, but these two components will actually sum up. Correct? So what is the area on which this pressure is acting? Look, here the flow area is A2, here the flow area is A1. So this part of the area which is not covered is nothing but total area minus this area A1. Correct? Yes or no? So this area which is not covered with fluid initially is A2 minus A1. Correct? So therefore, and you see the direction is positive, so plus P dash times of A2 minus A1 is basically here. Okay, so P dash times of A2 minus A1. So these are the total forces acting on the fluid. So this is equal to m dot out into V out in the x direction, which is V2, minus m dot in into V in, which is V1 actually, because at this control volume the fluid which is leaving is at velocity V2 and the fluid which is entering is at velocity V1. So now let us substitute these values here. I just want to tell you one assumption, that P dash value is almost equal to P1. This is taken from experiments actually by fitting pressure gauges. They have fitted one pressure gauge here and also pressure gauge here. So definitely they observed that this P dash and P1 values are very close to each other, and logically the reason for that is this enlargement is just beyond this uniform pipe, correct? So till here if the pressure is P1, then it takes some time for the pressure to settle till it means basically it takes certain length for the pressure to set up. So P dash, which is in this value, will be very close to the pressure at this location, and which is also observed same by the pressure gauges. Okay, so that's how this P dash and P1 is taken from the experiments. Okay, now if you substitute this, this implies P1A1 minus P2A2, P1A1 minus P2A2 plus this is again P1 times of A2 minus A1 is equal to m dot out. So m dot out and m dot in both are same because continuity equation has to be satisfied. So this can be written as rho A2 V2 square minus rho A1 V1 square. Okay, so this is what you have. Now you can simplify a few things. This A1 and P1 A1 gets cancelled because of this minus sign, correct? So we have P1 minus P2 times of A2. So P1 minus P2 times of A2 is equal to, let us do one thing, instead of writing it this way, because I want to cancel some terms, let us write it as m dot times of V2 minus V1. That m dot, let us write rho A2 V2 times of V2 minus V1. Okay, so let us write it here, rho A2 V2 times of V2 minus V1. So you can cancel this A2. If you cancel this A2, then the pressure difference is equal to between these two sections is rho V2 times of V2 minus V1 is what you have. Okay, so this is what you have basically. So the pressure difference between these two sections is identified as rho V2 times V2 minus V1. Okay, so that's it. You got this expression for P1 minus P2. Now let us simplify. Okay, so see here. Therefore, loss due to sudden expansion. Loss due to sudden expansion is equal to, loss due to sudden expansion is equal to HL, which is P1 minus P2 by OZ, which is rho V2 into V2 minus V1 by rho Z plus V1 square minus V2 square by 2Z. V1 square minus V2 square by 2Z. Okay, so this is what you have. So don't we need 2p dash? No, we don't need 2p dash because we have multiplied with the area. Okay, it's not like the two directions, it's like a complete circle. Okay, hi Shankar. So basically it's a pipe, correct? So whenever it's a pipe, we have multiplied pressure with area actually. So whenever we are multiplying area, we are taking the total area into consideration. No? So see here. At this case, we are multiplying P dash into the total area. 360 degrees we are covering already. Okay, so that's why we are not taking 2. Got it? Okay, here I have explained you for the top and bottom parts actually. That's the main intention. But actually if you see P dash, if you multiply, that is multiplied all over the 360 degrees of the flow. So that's why pressure into area gives you the component in the x direction. Okay. Like for example, you see here we are multiplying P into A. Similarly here P dash into the area which is missing. Okay, so that's it. Now if you simplify this expression, obviously this rho and this density cancels each other. So let us simplify this expression. So if you simplify this expression, if you take one G out, HL is equal to head loss due to sudden expansion is equal to 1 by G if you take out this slide. Okay, Shrikant, this one or the previous one? Yeah, any doubts please ask me. Okay, if you have any doubts you please ask me here. Okay, fine. Okay, so is this clear? Can we go ahead? Please type in the chat box, is this clear? Can we go ahead? Okay, this only, fine. So can we go ahead? So please type in the chat box. Fine. Okay, good. So HL is equal to, now if you see V2 times of V2 minus V1 by Z plus this V2 square, V1 square minus V2 square, that can be written as V1 plus V2 into V1 minus V2, A plus B into A minus B by 2Z. Okay, so if you see, we can take some terms out. If you take V1 minus V2 by G outside, for example, okay, so let us suppose if we take V1 minus V2 by G out, we have this V1 plus V2 by 2, correct here. So V1 plus V2 by 2, since we have taken minus of this sign, we have minus V2 here. So this is the expression, correct? Look, in these two terms, we have this V1 minus V2 term. So we have taken V1 minus V2 by G common, but here there is V2 minus V1. So there comes a minus sign here. So minus V2 plus V1 plus V2. So that's what we have here. Okay. So minus V2 plus V1 plus V2 by 2. So now if you simplify this expression, HL loss. Okay. So HL is equal to, so if you simplify this, we get V1 minus V2 by G times of, if you simplify this, V1 plus V2 minus 2V2. So total V1 minus V2 by 2. So therefore head loss in this case is equal to, head loss due to sudden expansion is, this is V1 minus V2 whole square, V1 minus V2 whole square by 2Z. So this is basically the expression for the loss that actually happens due to sudden expansion. Okay, so V1 minus V2, where V1 is the velocity at the small pipe and V2 is the velocity at the larger pipe. Basically when there is some expansion, then in the second pipe we have V2. So V1 minus V2 whole square by 2Z is what we have here. Okay, so this is the loss due to sudden expansion. Therefore head loss due to sudden expansion, head loss due to sudden expansion is equal to HL, which is equal to V1 minus V2 whole square by 2Z is what we have. Okay, so this divided with 2Z. Now I want to write one thing here. Look, this expression, if you see, we can, if I want to take V1 square out, for example, okay, so let us suppose V2 square out, generally what we'll do, V1 square out we'll take now. Okay, we'll take V1 square out. So if I take V1 square out, V1 square by 2Z, 1 minus V2 by V1 whole square is what we'll have here, correct? So 1 minus V2 by V1 whole square is what we have. Okay, if you take this V1 square by 2Z out, means from this expression, if you take V1 square out, we have 1 minus V2 by V1 whole square. Now from continuity equation, we have, from continuity, because I want to show one result to you, from continuity equation, A1 V1 is equal to A2 V2. So this implies your V2 by V1 is equal to J1 by A2. Okay, so this is what's the velocity, which is nothing but the area ratio that we have here. Okay, so here instead of this V2 by V1, you can replace with A1 by A2 actually. Clear? So therefore this head loss at the due to sudden expansion is equal to V1 square by 2Z times 1 minus J1 by A2 whole square. Okay, so this is what you have. So you can write any of these two formulas. Actually, if areas are given, you can write this, or else you can find velocity and you can write this expression. Anything is same. Okay, now I just want to give you one result here. So this is the case. Let us suppose, let us take the case of a pipe discharging into a tank. A pipe discharging into a tank, for example. Discharging into a tank. Okay. So let us suppose a pipe discharging into a tank, for example. Okay. So in that case, let us see what happened. A pipe discharging into a tank. So you have one small pipe. So let us suppose there is some large tank. Okay, so let us suppose if it's there is some large tank that's actually present like this, for example. Okay, this is some large tank that we have taken. Now this area is A1 and tank area is A2, for example. Let us suppose this area of cross section for this flow is A2, for example. Okay, so tank area, or basically if we say area of cross section, because this is area of cross section, this is also area of cross section, some large area of cross section of tank is, for example, A2. Okay, so let us suppose this is A2. Now let us see what happens here. If this is A2, look, if you want to calculate loss, here you can understand this as one point. Whenever the fluid is going here, you can call this as exit loss, for example. Okay, so because the fluid is actually exiting into this pipe. Okay, from this pipeline the fluid is getting exited into the tank. Okay, so now if you see, this is exit to tank, exit from pipe. Okay, better write this, exit from pipe, exit from pipe. So whenever this is exiting from pipe, this head loss HL is equal to, just now we have seen V1 square by 2G, where V1 is the velocity of the flow in this pipeline, into 1 minus A1 by A2 whole square is what we have. So here whenever this is a tank, can I say A2 value is very large as compared to A1? Yes or no? Can I say this? Because the tank diameter and the tank area is actually very large as compared to a small pipeline. Can I say this? Yes or no? So can we take this? Correct. Normally if some small pipe is discharging into a large tank, then definitely this large tank area is A2, then A1 by A2. Can I say that A2 is actually very large as compared to A1? So type in the chat box. Yes, correct. I can take this, right? Because obviously my A2 value is very much large as compared to A1. Now when this is the case, you can write, can you tell me what is the value of A1 by A2 in this case? Can you tell me what is the value of A1 by A2 in this case? This A1 by A2 value tends to which value? A2 is very large, so A1 by A2 value tends to which value? So type in the chat box, what is the value of A1 by A2? So means basically if A2 is very large, then A1 by A2 tends to means near to which value? So please type in the chat box. A1 by A2 tends to which value? A2 is very large quantity. Okay, 0. Correct. Obviously it tends to 0 because this value is very large. Okay, so A2 is very much higher than A1. So definitely A1 by A2 will tend to 0. So whenever A1 by A2 is tending to 0, then this implies exit loss. Okay, fluid is exiting from the pipe. So exit loss is equal to V1 square by 2G, which is the velocity of the flow in the pipe, of course, into 1 minus this A1 by A2 quantity turns out to be 0 square. So this gives you V1 square by 2G. Okay, so whenever a fluid is exiting from any pipe, the exit loss is basically equal to the kinetic head that actually available. Okay, so V1 square by 2G. Okay, so this is how we get the exit loss by doing this particular linear momentum equation analysis and also the Bernoulli's equation. Clear? So therefore loss due to sudden enlargement is equal to okay, so loss due to sudden enlargement is equal to basically V1 minus V2 whole square by 2G, and exit loss from pipe exit loss from pipe is equal to V1 square by 2g, which is nothing but the kinetic head of the fluid in this flow. Clear? So these are two important things that we could discuss here. Okay, fine. So is this clear to you? Okay, so I hope it's clear to you. Fine. So now let's go for this, entry loss, because we have seen the exit loss case. And normally, without doing all this analysis, because the analysis remains same even in case of sudden contraction in pipes. Okay, so instead of sudden enlargement, let us suppose you have the sudden contraction, then also everything remains same. Your analysis and all, everything remains same, but of course the sign changes and all. But finally, you will achieve the same expression. Okay, we will see what is that particular expression here. So second is losses due to sudden contraction. Losses due to sudden contraction in pipes. Losses due to sudden contraction in pipes. Okay, so let us suppose initially have a pipe in which there is some fluid flow. So first of all, let us try to draw the fluid. So now if you take this axis, so if you see here, let us suppose if there is some fluid which is coming and entering this pipe, for example. So let us suppose the fluid actually comes like this. Similarly here also the fluid actually, it travels like this, and just a minute. So let us suppose if there is a flow like this, for example. Okay, now so this is one section which is here. So section 2 at this point. Okay, so this is section 1 and section 2 1 and 2 actually. Now let us see if you have this pressure which is acting at this point is P2, for example, and pressure which is acting at this point is P1. This area is A1 and this area is A2. Okay, now if you see, just I want to tell you one thing, why streamlines actually cannot adjust like this is again because of inertia. Here the streamlines are bending actually because fluid wants to enter this region. So this bending will actually continue till certain distance, like how in the case of enlargement, if you see, in case of enlargement the fluid suddenly cannot enlarge, correct? It actually takes some span to spread over the area. Similarly here also, suddenly the fluid in this case suddenly cannot adjust to this complete area. So this bending of the streamlines will actually continue for some more time, and this basically, if you see from this section, at some location you will find the flow with minimum area. Okay, so this is the section. If you see section, this is basically section with minimum flow area, minimum flow area, and this is called vena contacta actually. Okay, which we will also see in orifice meter, but this is called vena contacta actually. Okay, so this is vena contacta, of course, and if you see, this is vena contacta. Now this section is 2 2, this is C. Okay, so here if you see, the area of cross section is AC, for example. Okay, now we define one thing which is called coefficient of contraction. We define something which is called coefficient of contraction. Coefficient of contraction, which is denoted with the term Cc. And what is Cc? Area at the vena contacta divided by area at 2. Okay, so this is area at 2 actually. Okay, means basically this area, which is of course the constant area anyway. So this area divided by, I mean this vena contacta area divided by this area. And who gives you the value of Cc? Normally you have tables. Okay, so from tables, depending upon the material of the pipe and all, we have certain values for the Cc. Okay, so vena contacta areas, which is done from the experimental results. Okay, so I'll show you basically coefficient of contraction tables. Normally you will pick the value of Cc from the tables. Okay, so coefficient of contraction tables. Okay, so if you see, coefficient of contraction tables is what we have. So from there we will pick the Cc value. Normally depends upon the diameter value, all these things. So you can take maybe this, you can see the images directly, you will get. So whenever it takes, it tells you about, means basically it depends on the diameter ratio d1 to d2, means it depends upon the pipe diameter to the small orifice diameter, means basically the small diameter d2 one, means basically if you see here, if you call this as d1 and if you call this d2, it depends on this ratio d1 by d2 actually. Okay, normally we use this many times in our research works and all, but just 1 by Cc value, if you see 1 by sigma, sigma is the pipe ratio actually, the standard notation, not the surface tension value. Sigma is basically this what do you say, 0.2 0.4 is nothing but d2 by d1, means let us suppose if the first pipe is 100 basically some 10 centimeters in diameter, the second pipe it converts to some 4 centimeters in diameter, so there is some contraction. So d2 by d1 value is 0.4, 0.6, 0.8 and of course 1. Basically whenever it is 1, then definitely there is no, you can see this picture for example, whenever this sigma value is 1, then definitely you don't have any contraction because the pipe is uniform pipe. Okay, fluid flows. So that's how we define this values of Cc from tables of course, but generally I just want to give you this region. Okay, so Cc is AC by A2. So this is vena contacta area, vena contacta area by A2. Okay, so I'm just what is A2 basically at this location. Now the main thing is, what is the loss? Head loss. So head loss due to sudden contraction is again same analysis to be done, but I'm not doing, I'm just giving you the result, which is Vc minus V2 square by 2z is what you will get actually. Okay, so vena contacta minus Vc velocity at the section 2 at the section Cc minus V2 by 2z. Vc is velocity of the flow, average velocity of the flow, average velocity of flow at vena contacta. Okay, so at vena contacta, at vena contacta. Okay, so now if you see, this Vc can be written as normally from continuity equation. So applying continuity equation, we can get, applying continuity equation, applying continuity equation, we get, so once you apply the continuity equation, we get A2 V2 is equal to vena contacta into Vc. So what can be written for Vc? Vc can be written as V2 times A2 by AC is what you can write here actually. Okay, so V2 times of A2 by AC. So if you replace this VC with that term, we get therefore head loss due to sudden contraction. Head loss due to sudden contraction. Head loss due to sudden contraction is equal to HL. And what about this HL? HL is equal to, you can see HL is equal to VC minus V2 whole square. So first of all, this 1 by 2G is constant outside. So let us write this VC minus V2. So what is VC? V2 times of A2 by AC minus V2 whole square, correct? Because from the continuity equation, this VC can be replaced with V2 into A2 by AC. So we got V2 into A2 by AC minus VC square. So if you simplify this result, then HL is equal to 1 by 2G times, if you take V2 out from this both expressions, V2 square, if you take out, we have A2 by AC minus 1 whole square. Okay, so what is the coefficient of contraction? CC is equal to AC by A2. Okay, so this we have CC is equal to AC by A2. So this value which is written here can be written as 1 by CC minus 1, correct? So this implies HL is given by V2 square by 2G, which means the velocity of the fluid in the pipe into 1 by CC minus 1 whole square. Okay, and normally for general values, this CC 1 by CC minus 1 whole square, this value will take some constant of 0.5. Okay, on an average they have given experimentally that this constant means the loss you can measure. So once you identify the loss, this constant they have found out to be 0.5 on an average. So therefore this HL in this case is given by HL is given by 0.5 times of V2 square by 2G, where V2 is the velocity of the pipe that is existing. Okay, so if you see, whenever there is some big tank or something, if the fluid is entering into some pipe, then entry loss is given by half of the kinetic head in this pipe actually. Okay, so 0.5 times of V2 square by 2G. And whenever this areas and all is very large, this loss is basically called the entrance loss or the entry loss. This is called entry loss because you see, generally in this case, whenever this diameters and all are very large, this is basically like fluid is entering from some reservoir to some pipe actually. Okay, so in such cases we get that this fluid is basically this value is basically 0.5. so that's how we have exit loss as therefore we have entry loss is 0.5 times of V2 square by 2G. Okay, so we have this clear. So that's how we get the answer. Fine. So this is simple analysis like what we have done. Same like the previous case we have to do. We should take this we should take this this linear momentum equation and Bernoulli's equation, and we have to work out certain things, okay, for getting this result. Clear? But here we introduce the concept of the vena contracta. So basically whenever there is certain sudden contraction, the streamlines cannot get submerged, the streamlines cannot adjust to the pipe diameter immediately. So the bending of the streamlines will continue to certain span actually, and then we have the things. Okay, so is this clear to you? So please type in the chat box, is this clear to all of you? Okay, if you have any doubts, you please talk to me, or else it's fine. Is this clear to all of you? So type in the chat box. So all of you type in the chat box, is this clear? Okay, clear? Then let's continue. So let us continue here. So flow measurement devices. Let us go to flow measurement devices. Okay. So let us try to get this flow measurement devices. So basically, how you measure the flow actually? Okay. So flow can be measured by very simple analysis. Like if you want to practically measure the flow, how you measure that? You take some container, you measure the discharge, you measure the time, so you will get the flow rate easily. Okay, but actually in these cases, how you measure the flow rate? Okay, so let us see how we actually measure the flow rate looking at the manometric deflections. Okay, we don't look at the measuring the velocities. Okay, so they actually directly measure the flow without giving you the talk about the velocities. Okay, so let us see what happens. So the first the three devices that we are going to look in case of this is Venturi meter, which is one very famous device, Venturi meter. Second, orifice meter. And third, in third case we don't do much analysis, I will just give you how the meter looks, flow nozzle meter. Okay, so this is flow nozzle meter is what you have. Okay, so this is flow nozzle meter. So let us see what are these meters actually, how we can actually get the discharge based on these meters. Okay, so let us try to see. First, Venturi meter. Venturi meter. So this Venturi is basically name of one, you know, Italian physicist. Italian physicist. So this is basically some Italian physicist. Okay, so he is Venturi, and this meter is basically developed by this this guy. So that's why it's given Venturi meter. So now Venturi meter, let us see what are certain good points about this Venturi meter. Venturi meter. Okay, so let us see this Venturi meter. Let's see what happens. Okay, so have you seen any Venturi meter practically in labs or somewhere? Have you seen Venturi meters? Please type in the chat box. Have you seen any Venturi meters actually? Seen? How many of you have seen a Venturi meter in your life? You might have seen that in fluid mechanics labs or somewhere. So please type in the chat box. Seen? So if you haven't seen, I'll just show you once. We have Google. So let us see. Venturi meter. Venturi meter. So if you want to see this Venturi meter, if you see a lot of a lot of videos and all animation videos are there if you want to see. So basically if you see, this is a perfect Venturi meter actually. Okay, so this is how the Venturi meter actually works out. Okay, so you can see this is the Venturi meter. Okay, now let us see. So basically all these are Venturi meters diagrams. Okay, so all these are Venturi meters diagram, datum or the reference line, whatever. So now if you see, this is how a Venturi meter looks. So normally Venturi meter is fitted in between a pipeline to measure the discharge. We actually use the technique of pressure difference for calculating the Venturi meters. Okay, so now let us try to see how a Venturi meter look like. Okay, so a Venturi meter, if you try to draw normally, let us suppose if this is the axis of the flow, for example, the Venturi meter consists of, let us suppose again you have the pipes as usual. So you have some pipe. Now you see we have a converging section. You have a converging section actually like this. Then you have some uniform section again. You have certain uniform section like this, and then you have certain diverging section. You have certain diverging section, and obviously if you see, for example, let me check this. So let us see this. Let me extend slightly. Okay, so now here again we have the pipeline that actually exists. Okay, so this is basically the pipeline. So this is the pipeline. Okay, so you have some converging part, then some straight part, and then diverging part actually. So this is how a Venturi emitter looks. This is how you fit this Venturi emitter in between a pipeline actually. Okay, now if you see, this is pipe and this is also pipe. So we have some things here. Look, this is basically a converging section. Converging section. This is some converging section. Then this part is called throat of the Venturi emitter, which is narrow, and this is the diverging section. Diverging section. Okay, so converging section, throat, and diverging section. Now if you observe one thing very carefully, in interviews and all, one famous question is, can you connect Venturi emitter in both the ways? Okay, can you connect Venturi emitter in both the ways actually? Can you connect Venturi emitter in both the ways? What is your opinion? Look, because pipe diameter is same, you will fix the Venturi emitter in between a pipeline. So whenever you are fixing it in between a pipeline, this diameter here and this diameter here both are same. So whenever if you want to fit, you can fit in any way. So can you fit Venturi emitter in any way? In both the ways actually. What do you feel? What is there any problem, or can we connect Venturi emitter in both the ways actually? So type in the chat box. So please type in the chat box. Can we connect? Can we connect Venturi emitter in any way in both the ways, or is there any particular way that we have to connect this Venturi emitter? No, we cannot connect. Why? What is the problem? If you can't connect, then why? What is the problem basically? What is the issue if you connect Venturi emitter in reverse way? Means let us suppose instead of this you have connected it the other way. Okay, length of Venturi emitter is same, both the ends will fit the pipe. Then what is the problem? What is the problem then? Pressure difference? No, actually pressure difference will be maintained same, because normally if you see in later case we will see pressure drop, which actually depends upon the friction factor, will depend on length and diameter. Length and diameter doesn't change here. There is one problem actually. Look, see here, if you see, you might have found out one difference actually here. See, this angle and this angle both are not same. Okay, so these angles are not same generally. Okay, so these angles are not same. So if you see here, this angle which is here is something around 8 to 12 degrees, and the angle which is here is something around 15 to 20 degrees normally if you see. Okay, diverging section and converging section. Yes, of course, if you see, look, even if you shift this, then also this section, whenever you fit this pipe in the reverse direction, then that pipe also acts as the converging section. Okay, and again this acts as the diverging section. But I will tell you what happens. If you see carefully, this cone angle is high. Okay, what happens when this cone angle is high? Let us suppose if the fluid is flowing in this direction. If the fluid is actually flowing in this direction, then connecting the converging section in this way means basically if you see, the higher cone angle in the upstream direction and the lower cone angle in the downstream direction, means basically if you take the throat as the reference, then in the upstream, normally if you see, upstream is before and downstream is after that particular point. Okay, so here if you see, In this upstream direction, if you have the converging section, then what happens is basically your within the small length, the area of cross section decreases very rapidly, correct? So within very small length that happened, the cross sectional area decreases from this value to this value very faster. So whenever the cross section value decreases very fast, then you have something called convective acceleration, which you have studied in fluid flows, correct? You remember this? There's something called convective acceleration. Of course, things are steady, nothing is changing with time, but if you see the case of convective acceleration, then definitely the convective acceleration term will be high in this case when you connect this higher cone angle in the upstream direction. Yes or no? Can you understand this? Higher cone angle should always be connected. Higher cone angle should always be connected in the upstream direction. Should always be connected in the upstream direction actually. Okay, so higher cone angle should always be connected in the upstream direction, so that the convective acceleration of the flow will be very high in this part, and whenever the convective acceleration is very high, then definitely fluid means this convective acceleration will make the flow to happen. Okay, so it actually drives the flow, understood? So that's the main reason. And also one more thing, one problem that arises here is, look, in this case, whenever there is some sudden enlargement, you can see there is one concept which is called flow reversal concept, which we will see later in boundary layer theories and all. So here if you see, there is some particles of the fluid which tries to fall back actually. Similarly here at this point in the flow, actually. Okay, so this flow reversal you have to have observed many times. Normally when water is flowing back from the dams and all, some particles of fluid will actually try to get back. Have you ever seen this? Normally, let us suppose if there is some big dam or something, if fluid is actually flowing down, then some part of the particles will actually try to travel in the back direction. You will see in the form of fog or something like that. Normally these tiny particles of water droplets will try to travel in the reverse direction whenever there is some sudden area available for the flow. This concept is actually called flow reversal, which happens in fluids. Okay, so that flow reversal also happens if you connect this cross section. If you connect this particular cross section, means let us suppose if the Venturi meter is like this, then what happens? There are two things that obstruct this. First thing, the convective acceleration will be very low, so flow actually sustains. At the same time, once the fluid reaches here, because of some higher enlargement, what happens? This streamlines will actually go in this particular direction. So streamlines will go in this direction. So obviously here there could be some flow reversal that can takes place. Okay, so this flow reversal should not happen actually. Okay, because if flow reversal happen, that's it, the flow cannot happen effectively. So that's why if you see here in this case in the upstream direction, such that in the upstream direction, so that okay, in the upstream direction, oh just a minute, so in the upstream direction, so that convective acceleration in the direction of flow, convective acceleration in the direction of flow is high, and it eliminates flow reversal. And it eliminates flow reversal actually. Okay, so flow reversal should also doesn't take place. Okay, and sometimes some common thing that you see in Venturi meters is size of Venturi meter d by d. This is what you will see, size of Venturi meter is d by d is what you will see sometimes. Okay, they'll give you 150 by 300 by 150, 150 by 100, they'll give you things like this. The meaning of that is This diameter is capital D, and this is capital D basically here, and this diameter which is here is small d. Okay, so if you see small capital D into small d, don't get confused. This capital D is the diameter of the pipe, small d is the diameter of the throat actually. Okay, so these are different things that you have to take care when you're talking about venturimeters. Clear? Got it? Fine. So first thing, you have to connect venturimeter only in a particular fashion such that the higher cone angle will be in the upstream direction and lower cone angle will be in the downstream direction. Okay, and because of these particular reasons, and if you find somewhere like this, then that meaning is pipe diameter is D and the throat diameter is small d. Now let us try to do certain small mathematical analysis to see how we'll get the flow rate. Okay, so let us see. Let us suppose you have the flow in this direction, for example some inclined case like this, so that you have your venturimeter. Obviously you have your venturimeter like this. Okay, so you have your venturimeter like this, then you have the flow, I mean you have the throat, you have the throat. Okay, and also you have this let us try to decrease the size of the diagram first of all, because I think I cannot fit the manometer again. So let us try to decrease this a bit. It should be higher cone angle. Okay, so let us see this. So let us suppose you have this case, and now you have the pipeline. So you have this pipeline. Okay, so once you have this pipeline, then there is some flow in this direction. So this is how the venturimeter is there. So basically it's an inclined pipe, so that there is some fluid flow. Okay, so let us suppose there is some fluid which is flowing in this particular direction. Okay, so there is some fluid flow. Now basically you want the pressure difference at these two locations. Okay, to calculate the discharge. So this is location 1 for example, and this is location 2 at the throat. They'll ask you why you will connect the manometer only at the throat and the pipe. Okay, so let me show you first of all how it is connected. So see carefully. So let us connect a manometer. So see here. Similarly, let us suppose you have one more this limb of the manometer. fine. So let us suppose this is the manometer. Okay, now you have connected this manometer at one end and also at the third. Now they'll ask you why you have connected manometer like this. Okay, why not you could connect this point at this location or maybe at this location? Because you see, if you want to have a uniform pressure, the velocity should be uniform. Okay, but if you connect this limb here or here, these ends are subjected to some acceleration of the fluid. Okay, so pressure fluctuations will be very high in these two locations. Okay, so that's why we do not connect any limb of the manometer between these two locations. We connect manometer limbs only at the locations of uniform flow diameter or uniform flow area. Otherwise what happens, if you connect this limb here at this location, there is some fluid acceleration, so then definitely there is some pressure variation that takes place, so that should not happen. Okay, now if you see, normally let us suppose if this is the direction, if you say for example P1, if you say for example P1 is the pressure here, so P1 and P2 are the pressures at these two locations. For example, means basically at this location you take P2, and let us say at this location also, because normally in case of pipes you will come to know in 7th chapter there won't be any radial variation. Okay, so let us suppose if there is P1 here for example. Okay, so this is P1 and this is P2. Now let us suppose this is a mercury manometer, so we have filled some mercury. Okay, let us suppose if P1 is greater than P2, let P1 greater than P2, P1 greater than P2. So whenever you have this P1 greater than P2, you have the mercury manometer. So let us see. Similarly, if P1 is actually greater than P2, then in that case this manometer limb will be somewhere here, for example like this. So this is basically the manometer. Okay, so because of the pressure there is some deflection in this manometer, and obviously there is some fluid which is flowing in this. Okay, so there is some fluid which is which actually flows in this case. Okay, okay, so there is some fluid flow, and here obviously this is filled with fluid. This is filled with fluid, this is also filled with fluid actually. Okay, so this is also filled with fluid. Now how you calculate the volume flow rate using this deflection? So let us suppose the mercury manometer has shown certain deflection here. Okay, so let us suppose this has shown certain deflection, mercury manometer has shown certain deflection to you. Let us suppose this deflection shown by this manometer is H for example. Then how, using this H, how you calculate the flow rate? Okay, you know this diameter, you also know this diameter. Okay, now let us see how you calculate this. You know the size of the Venturi meter, it's D by D, means basically pipe diameter is D and third diameter is small d. Now how will you calculate this flow rate actually? Okay, so let us see that. First of all, you know flow rate can be written as A1 V1, and which can also be written as A2 V2, means if you can find either V1 or V2, that's it, your story is done. Okay, so now let us see, applying Bernoulli's equation at points 1 and 2, assuming no losses, but normally what happens, there could be some frictional loss. Okay, so assuming no losses, then applying Bernoulli's equation, at points 1 and 2, at points 1 and 2, actually. Okay, so if you apply Bernoulli's equation at the points 1 and 2, then let us see what happens. P1 by rho z plus V1 square by 2z plus Z1 is equal to P2 by rho z plus V2 square by 2z plus Z2. This is what you have from the Bernoulli's equation if you neglect losses. Okay, and let us suppose the separation between these two. These 2 points, let us suppose these 2 points, they are separated by some distance from some reference. Let us suppose this point is at a height z1. This point is at a height z1 from some reference which we don't know, and this point is at some height z2 from with respect to some reference whatever you have taken, such that the difference between these two is z2 minus z1. Okay, now how to convert this? So here if you see, we write something which is equal to p1 by rho z plus z1 plus v1 square by 2z is equal to p2 by rho z plus z2 plus v2 square by 2z. So this heads which are here are due to static pressure plus this datum. So this is called piezometric head p1 star. Okay, so p1 star by rho z is what we say here. P1 star is basically the piezometric head. Okay, so this similarly here, this is the piezometric head p2 star by 2z. So these are called piezometric heads. Okay, so they are called piezometric heads at sections 1 and 2. Okay, so they are called piezometric heads basically. Okay, so these two are called the piezometric heads. Now if you see from this manometer, what you can understand. Okay, so see here, let us suppose if this vertical separation between these two is actually z2 minus z1, at the same time let us suppose if this distance between these two sections is y, for example. Okay, y or x, whatever you take, for example y. Okay, now if you see from manometer, what can you write? From manometry, let us see what comes out from manometers we have seen in hydrostatics. So now if you take this as a reference section, so let us suppose if you take this as your reference, for example, so let us suppose if you take this as your reference, so pressure at this location, so pressure at this location and pressure at this location should be same, correct? So what is pressure at this location? P1 plus basically if you see P1 plus there is some height which is for example say this height we have taken. What is this height we have taken? So let us suppose if this is the datum, so P1 plus rho g z1 let us take for example. Okay, so P1 plus rho g z1 is the elevation that you take for example. Okay, so okay, let us take this as the datum, then no need of this y generally because that's get eliminated anyhow. So let us suppose this is the datum you have taken. So from this point this height is at a height of z1 and from this point this is at a height of z2 for example, let us say that. Okay, so from manometry if you call these points A and B, PA is equal to PB. So what is PA and PB? Let us see here. From manometry, PA is equal to PB. So what is PA? PA is nothing but P1 plus rho z z1 actually. Okay, so let us take this point directly. P1 plus rho g z1. So P1 plus rho g z1. This is equal to, at this point PB pressure is P2 plus rho g z2 minus h. So P2 plus this fluid column pressure. So this fluid column is nothing but z2 minus this small h. So z2 minus h. So we have rho water, rho fluid. Okay, so let us say rho fluid for example. This is the working fluid. So g z2 minus h plus this manometric pressure due to h. So rho manometric fluid gh is what you have basically. Okay, now if you see we can cancel out few things here. We can adjust few things actually. So if you see, if you divide this complete equation with rho z, then P1 by rho fluid g plus z1 is equal to P2 by rho fluid z plus z2 minus h is what you have plus rho manometric fluid by rho fluid times h. This is what you have, correct? So now if you bring these terms to the left hand side, we get P1 by rho fluid z plus z1 minus P2 by rho fluid z plus z2. So this total difference of pressures is actually equal to, these two terms are left on this side. So if you take h out, h times of rho manometric by rho fluid minus 1. So this is what you have basically. Okay, so this is the piezometric, and I told you just now this is the piezometric head, P1 star by rho g minus this is P2 star by rho g. This is equal to H times of rho m by rho f minus 1 is what you have here. Okay, so this is the equation which is actually present. Okay, so this is the case. Now if you replace this pressure difference at these two locations, then means basically if you shift this equation to the means if you shift this term to the left hand side and if you shift this to the right hand side, then let us see what comes out. So therefore we have P1 star by rho g minus P2 star by rho g is equal to P1 star by rho g minus P2 star by rho g is equal to V2 square minus V1 square by 2g. V2 square minus V1 square by 2g actually. Okay, now if you simplify slightly, this equation implies this piezometric difference from the manometers is obtained H times of actually rho m by rho f minus 1 is equal to V2 square minus V1 square by 2g, or if you multiply 2gh, for example if you multiply 2g here on this side, 2g if you multiply on this side, we have V2 square minus V1 square. This equation is actually important for you. Okay, because if you see, therefore V2 square minus V1 square is equal to 2gh times of rho m by rho f minus 1. Now you can see this basically here, V1 and V2 can be written as V1 can be written as 4q by pi d square and V2 can be written as 4q by pi small d square. Correct? Yes or no? Because you see at section 1 this is the diameter. So if you have a discharge q, for example, then q is equal to this velocity at this section V1 into this area which is pi by 4 capital D square. Similarly here discharge is equal to A2 which is pi by 4 small d square into V2. So here you can write this V1 and V2 expressions in this case. Okay, so now if you substitute here, instead of writing in terms of diameter, let us do one thing. Let us keep in terms of areas, which would be better, q by A1 and q by A2, because otherwise terms will be very large unnecessarily. So now if we substitute these expressions here, we get q square by A2 square minus q square by A1 square is equal to 2gh times of density of mercury manometric fluid by density of flowing fluid minus 1. So from this expression, if you take q square out and if you take LCM, A1 square minus A2 square divided by A1 square into A2 square is equal to 2gh times of manometric by flowing fluid minus 1. So what is the expression for discharge from this case? So discharge is equal to, if you simplify this, if you shift this term to the left hand side, we get J1 A2 by square root of A1 A2 by square root of A1 square minus A2 square, A1 square minus A2 square into square root of 2gh times of manometric fluid by flowing fluid minus 1. So this is what you have. Clear? So this is the theoretical discharge what you have calculated. Okay, so this is the theoretical discharge, of course. Okay, so whatever the discharge you have calculated in this way, this is basically the theoretical discharge. Theoretical discharge. Okay, simple. We have applied the Bernoulli equation and the continuity equation. That's it. Okay, continuity also we haven't applied anywhere. Just we have taken this V1 and V2 in terms of Q, but this Z1 Z2 difference is taken in terms of piezometric head, which can be obtained from the manometer again. Okay, so from manometer this is the case, so therefore we have substituted, and this is the theoretical discharge that you have calculated using this concepts of Venturi meter. Okay, but in actual case what happens? In actual case, because of some of the pressure this friction involvement and all, the discharge what you will actually get if you measure will be less. Okay, so therefore actual discharge is given by something called coefficient of discharge. Coefficient of discharge. coefficient of discharge, which is generally denoted by CD in this case. Okay, so CD, so this CD is actually equal to actual discharge by theoretical discharge. Okay, so actual discharge by theoretical discharge. Okay, so this is what we have, and normally for Venturi meter this value lies something around CD of Venturi meter is around 0.9 to 0.94 sometimes to 0.98 of this range on an average. Okay, it has very high coefficient of discharge. Okay, means whatever you have calculated using formula, that will be very close to the actual discharge. Only some 5 to 6% variation will be there. That's why Venturi meter is one of the most famous meter that is used to measure the flows even till today. Okay, and now if you see one thing, to calculate this expression you need not do anything. Very simple. Look, once you know the Venturi meter, you know the pipe, this A1 is fixed, A2 is fixed, correct? Because you know the diameter of the pipe, you also know the diameter of the third, because you know Venturi meter and pipe initially. So A1, A2 is known to you. You know which fluid is flowing in your pipe. You also know the manometric fluid in the mercury manometer that is present. So all these values are fixed. Just when you rotate the valve and if you change the flow rate, only thing that changes is this H. Okay, so normally in labs and all, when we were doing experiments in IIT Madras or somewhere, how we used to do is we will generate an Excel such that all this data is constant, correct? This is constant for a given setup. Yes or no? If you have a pipeline, if you have a Venturi meter fixed, then A1, A2 are fixed values. This OM is also fixed because manometer you cannot change every time. So manometric fluid is also fixed, and this 2G is constant. This fluid delta F if you change, and flow rate if you change, this H actually changes. So we will keep two columns empty for filling. One is density of fluid and one is H. Let us suppose if you are filling water, 1000 is fixed. Okay, if you are filling gasoline or something, in case of diesel engine experiments and all, we will fill gasoline sometimes, then we will get this. Okay, so we have very small Venturi meters also, okay, to understand the flow of gasoline engines, all these things. So this is the formula that you get for the theoretical discharge. Okay, only thing that you have to take is this H from the manometers. Whatever the deflection you see in the manometers, you see outside, like for example, you see whenever you connect a manometer, you will see certain difference in the limbs. So this difference, one scale will be fitted here, so you can see what is the deflection in the manometer, so that once you find the deflection in the manometer, you can easily calculate what is the discharge that actually happens to the Venturi meter. Okay, if you know the value of CD, then actual discharge is this value multiplied with CD gives you actual discharge. Clear? Okay, the only thing is we need to apply the concept of manometers. That's it. Okay, any doubts? We have spent almost some 40 minutes on the Venturi meter, but actually this mathematical analysis is fine, but initially some good theory points what I have told you, they will be asked in many interviews. They'll ask you, can you connect Venturi meter in any way? Okay, what is wrong if you connect, pipe gets matched, so what is the problem? They'll ask you these kind of questions. Make sure you answer them. Okay, because this formula is anyhow it's fine. Okay, so type in the chat box, is this clear to you? So fine, we have just taken the mercury manometer balance, that's it. Okay, so if you want to see this Venturi meter thing, what we have done, we have taken basically some Venturi meter which is flowing in that case. Okay, so in that Venturi meter we have applied this Bernoulli equation. So when you apply this Bernoulli equation, this piezometric head has to be identified. So with this piezometric heads difference we identified from the manometers. Okay, so from manometers, if you see the pressure at those two locations should be same. So whenever the pressure at these two locations is same, then we got this hydrostatic law. So when we got this hydrostatic law, then we have basically simplified this result and achieved this value. So we have substituted here and we have simplified. That's it. By substituting V1 is equal to Q by A1 and V2 is equal to Q by A2, we have substituted, and this is the correct answer what we have got. Okay, so this is the concept of Venturi meter. Okay, so tomorrow we'll see all phase meter, because I think only some 1-2 minutes is left. We cannot start now. So we'll see all phase meters, and also we'll see one very important velocity measuring device, which is pitot tube. Okay, so this pitot tube is also somewhat important in airplanes and all. Even till today some pitot tubes are used for measuring the velocity of the airplane and all these things. Okay, in terms of knots of course. So that's really some important thing again. So we will go through all these things very soon. Okay, in tomorrow's session. Clear? Okay, so hopefully tomorrow I think we can conclude this chapter if things go fine. Okay. It takes some 5 I know, I think 4 lectures are done, so maybe 2 more lectures it may take. Almost some 6 lectures it may take, but we'll finish off the things. Okay. So fine then. If you have any doubts, you can ask me regarding anything that we have discussed today. So if you see, these are the things that we have talked since the beginning. We have used this case of angular, basically this sprinkler case, and then we have used this bend, basically on some bend, how you calculate whenever there are some pressure forces that are acting, how you take this into picture. Then we have talked about this sudden enlargement in pipes, sudden contraction also we have talked, entry loss, exit loss we have talked, and then we moved on to this flow meters. Then we have talked about this Venturi meter. That's it. These are the things that we talked about. Okay, so no more doubts. If you don't have any more doubts, then we shall end this session. Clear? So fine then. So tomorrow we'll talk about this orifice meter, and also we will talk about some pitot tubes and some tanks emptying time, all these things. We will talk about some projectile motion also. Once again, we will consider that projectile motion, and mostly these things will finish off the things for this chapter. Okay. Fine then. Okay. Fine then. Take care. We'll meet tomorrow at 7 o'clock, right? 7 p.m. is the class. 2 classes we have missed on Friday. So yesterday and today we have we have taken one extra class. So tomorrow at 7 p.m. Okay, no extra classes. Clear? No doubts. Okay, fine then. Thank you all. We'll meet tomorrow at 7 p.m. Okay. Take care then. Take care. Bye all of you. Good night. Please meet at 7 p.m. tomorrow. We'll continue our discussion. Okay. Thank you all. Thank you guys. Bye. Take care.